Good morning, ladies and gentlemen. My name is John Moroney. I'm the Business Support Manager for HACH in the UK and Ireland, and just wanted to welcome you all to the second in our current series of webinars from HACH on wastewater applications. The presentation this morning will last approximately 20 minutes, and as always with our webinars, we'll keep the questions until the end of the presentation, when we'll answer them, and if need be, we'll take them offline and discuss further. The way to ask a question is to type it into the panel that you see on the left-hand side of your screen, and as I said, we'll look at those at the end of the presentation. The second presentation in our series this morning is entitled Oxidation, Ditches and Alkalinity. It's presented by Martin Butterfield. Martin is one of our application development managers in the UK and Ireland, and he's a real-time control optimization specialist. He's worked in the water industry for over 30 years now and has been at HACH for the last 20. So he's got a wealth of experience to bring to this subject. I'll hand over to Martin now, who will go through the presentation, and I'll speak to you all again at the end. Over to you, Martin.
Thank you, John, for your introduction. In today's webinar, I'll cover a short history of oxidation ditches, their advantages and disadvantages, an outline on their design and possible modifications, their ability to nitrify and denitrify wastewater, and also alkalinity issues around nitrification in combination with the lower phosphorus consents that are coming in. The oxidation ditch was the brainchild of Dr. I.A. Pasveer of the Netherlands, who in 1954 had the first sloot, which is Dutch for ditch, constructed in Delft. This first sloot had a treatment capacity of about 600 PE and had an operating cost of less than 50% of the existing technologies of the time. His idea was to mimic nature in a controlled environment, but more importantly, this would be a low-cost system enabling small communities to treat wastewater before discharge to river. As you can see from this black and white picture taken at the time, it is clear why the treatment system was called the ditch. It can also be seen there is no health and safety considerations, but anyone not looking where they were walking could have a very unpleasant surprise. Also visible in this ditch is a horizontal aerator, which he also designed. And this is there to aerate and impart flow to the liquors of the ditch. Sources have it that the company that Dr. Pasveer worked for never registered the design of the ditch and hence never really made any real money from his idea. Unlike Dr. Pasveer's prototype, most oxidation ditches are at least or in part above ground. Depth of ditches vary from 1.5 to around 5 meters, although at these extreme depths, the brush-type aerators are unlikely to be able to impart sufficient velocity to the mass of the liquid contained within the ditch without the assistance of mixers. The velocity of the mixed liquid within the ditch should be at least 0.3 meters per second to maintain solids in suspension. In essence, the design of the ditch has changed very little. Most ditches still use brush rotors, but due to the wider channels used, curved baffles are added to the ends of the ditches to maintain the velocity of the mixed liquors and prevent solids being deposited on the inside of the bends. Oxidation ditches are fully mixed systems, operating with a much longer hydraulic retention time than that of a plug flow ASP, and can be designed to operate without primary settling tanks. They are generally considered to have a larger footprint than a conventional plug flow activated sludge plant, and are therefore more suited to smaller rural catchments. Although we give an example at the end of this webinar, which actually doesn't follow this statement. The surface aerators installed provide a dual purpose of not only entraining air, but also provide a velocity to the mixed liquor. and it is important to ensure the velocity of the ditch is sufficient to maintain the solids in suspension. These relatively high velocities are not required in a conventional plug flow ASP. Another difference between ditches and ASP is that they operate with much longer sludge ages. The advantages of oxidation ditches are they are considered to be simple to operate. With their long hydraulic residence times, they are resistant to both shock loads and washout incidents due to the volume of the mixed liquor contained within the ditch that dilutes any shock load or toxic event. Control is usually only by dissolved oxygen. However, if denitrification is required, redox or ORP measurement can also be used to indicate the change from the oxidizing conditions where ammonium is converted to nitrate and the condition when nitrate is reduced to elemental nitrogen. The typical redox values are as follows. For the oxidation of ammonium, this occurs in the ORP range of plus 50 to plus 325 millivolts, and the reduction of nitrate to nitrogen takes place at redox potentials between plus 50 and minus 50 millivolts. You may have noticed that there seems to be both nitrification and denitrification can take place at the same time when the redox potential is at around 50 millivolts. This is correct, as an anoxic zone requires a DO concentration of less than 0.3 milligrams per litre to operate, but even at this low DO concentration, some nitrification is still taking place. For the ditches that are required to nitrify, the extended sludge age of an oxidation ditches promotes the growth of nitrifiers, which are much slower growing than the BOD consuming heterotrophs. There are a few downsides though. Most oxidation ditches are operated on the safe side, with generally no operator around, so are usually operated with all the aerators running to ensure low ammonium concentrations are exiting the ditches at all times. As they are fully mixed systems, they have a low F to M ratio and therefore are prone to favour filamentous bacteria, which can cause foaming and bulking solids in final clarifiers. The following two slides show aerial photos of ditches with all aerators operating. This is a large plant containing 3 oxidation ditches, and as can be seen by the white aerated water, all 6 aerators are operating in each of the 3 ditches. We are familiar with this particular plant, and it is heavily loaded. However, all 18 aerators were still in operation overnight when the load was at its minimum. We will return to this plant later within this webinar. At this plant, only 2 of the brush aerators are in operation. However, the rotors are being supplemented by fine bubble diffused aeration, covering over half of the ditch. As mentioned earlier, oxidation ditches are fully mixed systems, and as such have a low F to M ratio within the ditch, which can promote the growth of filamentous bacteria. In plug flow activated plants, an oxidation zone, an anoxic selector zone is often used to provide conditions that favour the growth of the flock-forming bacteria over the filamentous bacteria. One way of limiting the growth of filamentous bacteria within an oxidation ditch is to ensure that sewage and RAS enter the ditch in an anoxic zone. In the previous aerial photos of the ditches, this would probably not be possible. In these cases, an external anoxic zone to promote the flock-forming bacteria could be used to both provide conditions favouring the flock-forming bacteria and also provide conditions for denitrification, if combined with an internal recirculation from a section of the ditch that is low in dissolved oxygen. We will cover this in more detail later in this webinar. The next 4 slides cover the most commonly used aeration systems in oxidation ditches. Brush rotors are probably the most common. They can provide an oxygen transfer efficiency of up to 2 kilograms per kilowatt hour, although this seems to be poor when compared to fine bubble diffused aeration, with claimed oxygen transfer rates of between 2 and 8 kilograms per kilowatt hour. However, it should be noted that the brush rotor is also imparting a flow to the mixed liquor, and when used, for example, in a 2 meter deep, 5 meter wide ditch, the rotor is not only aerating the mixed liquor, but is moving in the order of 3 tons per second. Brush rotors are installed along with a submerged baffle to deflect the flow of aerated water towards the base of the ditch, causing turbulent flow, providing both mixing and the required velocity to maintain solid suspension. The location and angle of this buffer is critical for the efficiency of the aerator, and being submerged, this is a vital piece of infrastructure which is often forgotten. It's also noted that in the UK and Germany are the largest users of brush rotors in Europe. However, brush rotors are considered to be an old technology by many manufacturers. All forms of mechanical aerators produce mists or aerosols, which not only promote odour issues, and covers all equipment within their vicinity with a thin coating of dried sludge, making displays pretty much unreadable. Brush rotors are often covered to reduce this misting, but I'm not able to say if this reduces the efficiency of their operation. Another drawback of these aerators is that they entrain atmospheric air, which in severe weather conditions can significantly cool the body of water, despite the amount of energy being put into the system. This is in direct contrast to diffused air systems, which tend to heat the body of water. Some sources state that up to 4 degrees centigrade of cooling of the body of liquid by evaporation is possible. This cooling effect can have a significant effect upon the nitrification rates in the winter months, when temperature of the liquid within the ASP is already reduced. Another option for horizontal shaft aerators are disc aerators. It is claimed that these are more energy efficient, reduce misting and noise, as the surface of the water is not being repeatedly hit by a large number of blades. Because of the reduced misting, it is also possible that the cooling effect is also reduced. Both brush and disc aerators are relatively easy access for servicing, as there is no need to drain the tank in which they operate to carry out routine maintenance of the aeration system. Other forms of mechanical aeration are available, including spiral aerators, which impart a velocity to the water, and vertical shaft aerators, which offer higher energy efficiencies but also require mixers to move the body of water around the ditch. Currently, horizontal shaft aerators are the most common form of aeration within oxidation ditches. The options for the control of the amount of oxygenation generated by brush aerators are limited. The rotational speed can be altered using a variable speed drive, but this would reduce the velocity of the mixed liquor within the ditch, so turn down is limited. Alternatively, the level of mixed liquor within the ditch can be adjusted via the outlet weir. But if the water level is too low, then this again reduces the velocity. And raising the level too high can result in excessive load on the drivetrain of the rotor, and can also reduce the oxidation transfer if the rotor is too deeply submerged. In ditches with multiple aerators, a simple answer for high DO is to simply turn one of the rotors off until the DO drops to a normal level provided the velocity of the ditch is maintained. Most plants will operate with all rotors operating to ensure compliance. In fact, they are generally over-aerating and wasting energy. It's now becoming more common to install fine bubble diffused aeration in oxidation ditches, making the aeration of the contents of the ditch much more controllable and reducing the intensity of aeration does not impact upon the velocity of the mixed liquors within the ditch, and this has to be supplied by submerged mixers. When installed within the ditch, fine bubbles are also have a longer contact time than with mixed liquors than they would in the similar depth ASP due to the velocity of the ditch, and this enables improved gas transfer. Also, unlike diffuser grids in plug flow plants, the FBDA grids used in oxidation ditches are smaller and can be lifted from the ditch without the need to drain the contents, making servicing of the diffusers much easier. As I've mentioned previously, oxidation ditches are considered to be simple to operate and maintain. Generally, the only measurement made in the ditch is dissolved oxygen, and to a lesser extent sometimes mixed liquors. However, there are issues with measuring DO in an oxidation ditch. In a plug flow ASP plant, the measurements of DO are made along the length of the lane to ensure the target DO concentration is met, and hence both BOD and ammonium concentrations are decreased as the mixed liquor passes down the length of the lane. The amount of air being introduced into each section or zone of the lane is controlled by a number of diffusers in the zone, with the highest density being at the start, and also controlled by the limiting the volume of air being supplied to the diffuser grid. This is not the case in an oxidation ditch, where the contents again are fully mixed, and as the mixed liquor is transported through an aerated zone, the DO increases. After exiting that aerated zone, the DO is depleted as the biomass consumes oxygen. A diagrammatic interpretation of this is shown in the following slide. In these two diagrams, the red vertical bar on the left-hand side represents the aerated zone, this being either a rotor or FBDA zone. And as the mixed liquor travels away from this zone and around the ditch, the DO concentration reduces as the biomass takes up the oxygen. In low conditions, for example overnight, the oxygen gradient will be represented by the upper diagram, and this could be considered to be the endogenous respiration rate of the biomass. The lower diagram represents the same oxidation ditch in high-low conditions. Here the oxygen gradient represents the biomass in a luxury uptake state and feeding on the incoming BOD and ammonium load. So therefore there is no location for a DO probe within the ditch that provides a representative value of the dissolved oxygen concentration. So although DO concentration is important, HACH would recommend that consent parameters, that is ammonium or nitrate, are measured to comply with consent. Moving on to denitrification. Just as in a BNR plant, oxygen can be recovered from the nitrate formed in the nitrification of ammonium load by the use of an ANOXIC zone within an oxidation ditch. For example, if there was 14 milligrams per litre of ammonium as N present in the inlet, then this would be fully nitrified, means that of course there is still 14 milligrams per litre of nitrate as N present in the ditch. But that 14 milligrams per litre of nitrate contains the equivalent of 48 milligrams per litre of oxygen, and that is available for BOD removal. And this is a dissolved oxygen concentration that could never be achieved using air in an aqueous solution. If ANOXIC zones can be formed within the ditch, then this combined oxygen can be utilized for BOD removal by the heterotrophic bacteria within the biomass and hence saving energy. One thing to note is that denitrification is a zero-order reaction. This means that the rate of denitrification is independent of the concentration of nitrate, but is dependent upon the availability of BOD and the DO concentration. The zero-order reaction kinetics hold true until the concentration of nitrate drops to very low levels. In previous webinars, my colleague Stuart Ainsworth has covered issues with alkalinity, mainly concerning nitrification and phosphorus removal. The same things apply equally to oxidation ditches, and processes of nitrification depletes alkalinity. For every gram of ammonium converted to nitrate, 7.14 grams of alkalinity are consumed. In regions with low natural alkalinity, and especially if dosing acidic metal solutions for phosphorus removal, there is a risk of low pH within the ditch due to the complete destruction of the natural alkalinity content of the water. Unless the process has become specifically acclimatized to operate at low pH, nitrification usually stops at around a pH of less than 6.5, making alkalinity and the control of pH a critical parameter, especially in soft water areas. By introducing ANOXIC conditions, either in the ditch itself or an external ANOXIC zone, half of this consumed alkalinity can be recovered, which can mean alkalinity dosing may not be required. HACH'S approach to the control of oxidation ditches is to measure the key parameters for consent, that is ammonium and nitrate. By monitoring and controlling these parameters, consent compliance can be assured. The control system can be limited by the DO concentration required by the client and by applying minimum and maximum DO limits to the controller. By controlling the intensity of aeration, the size of the aerobic and anoxic zones within a ditch can be modified to suit the required level of treatment, and to which the key parameter of treatment is required. This slide shows a schematic of the HACH system for controlling an oxidation ditch. In this, ammonium and nitrate are measured close to the outlet weir. The real-time control system has a target values for both ammonium and nitrate and a weighting factor for both. So for instance, a site that has a total nitrogen consent of say 10 milligrams per litre, the RTC will be set for ammonium concentrations of around 3 and a nitrate target a concentration of say 5, but weighted towards ammonium. If the measured ammonium concentration is over 3, but the total nitrogen consent is less than the consent, then the RTC will increase the aerobic volume of the ditch to nitrify the ammonium. As the ammonium concentration reduces to below 3 milligram per litre threshold, the RTC will then reduce the aerated volume of the ditch by reducing the aeration intensity output and therefore increase the size of the anoxic zone in the ditch, thus reducing the nitrate content and keeping the site within its total in consent. You may also have noticed that there is a dissolved oxygen measurement being made by the RTC. This is to override some of the control of the RTC to ensure the DO concentration at a location chosen by the site is always between customer selected values. The following two slides relate to a HACH oxidation ditch controller operating within the UK. This was a heavily loaded plant with a population equivalent of 250,000. The aeration systems were both rotors and fine bubble. Power consumption of this plant was close to 27,000 kilowatt hours per day and has an ammoniacal ammonium consent of 20 milligrams per litre with no total end consent. Here we have a slide showing the actual ammonium and nitrate concentrations in an oxidation ditch where RTC is in control. The data covering a period of 4 days in April this year. This is a heavily loaded plant which, before RTC was installed, operated with aeration at 100% throughout the whole day. The dark blue line is the aeration intensity required as calculated by the RTC software, which is applied to the aeration system. The red line is the ammonium concentration and the green the nitrate. The extreme left of the plot shows aeration intensity at 100% with the ammonium concentration within the ditch reducing. As the resulting increase in nitrate concentration. When the ammonium concentration has reached 5, the aeration intensity is reduced to 25%, which is by reducing the rotor speed to 25%. This results in the formation of anoxic zones and the subsequent destruction of nitrates by the heterogeneous bacteria. Using the oxygen from the nitrate for the oxidation of BOD. During the 4 days shown, the aeration system only operated at 100% for 49% of the time, and 25% of the time the aeration system was operating at or below 50% aeration intensity. During all of this time, the plant never exceeded more than 12 milligrams per litre ammonium with a consent of 20. Therefore, this energy saving was achieved at no risk to compliance. There may be additional unseen benefits of lower stress on the mechanical drives as well. The results of installing HACH'S RTC system on this site were really quite impressive. A 30% energy saving with the site and still compliant on ammonium. An energy saving of around £230,000 a year is possible, and there are further energy savings to come once the system has been fully optimized. For sites where it is not possible to introduce an anoxic zone within the ditch, an external anoxic zone can be created by mixing settled or screened sewage with returned activated sludge in an external chamber and using an internal recirculation from a low DO region of the ditch to achieve de-nitrification. The HACH oxidation ditch controller can still operate on the ditch in conjunction with the internal recirculation controller to de-nitrify the mixed liquor, but limit the returns when DO concentration is high in the ditch, so as not to introduce too much oxygen within the anoxic zone and hence limit the zone's ability to de-nitrify. Thank you very much for that. That concludes my part of the webinar.
Thanks, Martin. Thanks very much for that. Very interesting presentation. Just to remind everybody about questions, if you do have any, there is a window on the left-hand side of your screen. Please type a question in there, and then I will see if Martin can answer you. If not, we can take them offline later on. First question, Martin, we've got in is, would you operate an oxidation ditch on redox potential alone?
Thanks for that. That's interesting, actually. I mentioned redox, and I know it is used in some plants, but the issues really are that what we're trying to do is measure consent compliance, and that's really what our RTC systems are there for. They primarily go for compliance before energy saving, whereas with the measurement of redox within a ditch, although you are looking at the redox potentials, then you don't have an idea of the actual ammonium or nitrate concentrations that are there, only that what the potential is. So I would be guarded about using redox as the main control in that respect, because once the mixed liquors have exited the ditch and through the final settling tanks, then you've got no control of the system.
Right. Okay. That's good. Thanks for that. The next question I've got in here, I'll try to interpret it, but it says, I think the person means, would I have a conversion factor between measured ammonium, NH4N, and an ammonia consent compliance figure in NH3?
NH3 and NH4, yeah, the ratio is just 18 to 17, NH4 to NH3. That's a simple conversion factor, but I'm not sure if that's really what the
No, I'm not. I'm not sure either. I mean, the other thing to say here is obviously the ammonium monitors we're talking about they can be set up to either read NH4 or NH4 as N. So either can be displayed and used from that point of view. Can you elaborate a little bit more on that side of it, Martin?
Yeah, quite often the consents, certainly in England that I'm familiar with, are in as N, and so the ammonium monitor would, whoever's manufacturer it is, will convert to a concentration in N, and it's really is just a mathematical conversion. We talk about ammonium because that is the state that ammonia is in when dissolved in water. Ammonia is in H3, and that's the gas, and that's the gas that you get in smelling salts is the common example. But when it dissolves in water, it becomes the ionic form, NH4+, and that's what's measured. So that's why you see it, the ammonium analyzers measuring it as NH4 as N, and just taking the nitrogen content of that.
Okay, I think that explains it further. If that doesn't answer your question, then obviously please retype into the box and we'll readdress. The next question is: do we have or do you have any further advice on controlling foaming filamentous bacteria?
Yeah, that's difficult. The use of an anoxic zone and selector zone is obviously the way most of this is done. Keeping filamentous bacteria under control is quite an issue in some sites. Low DO can also tend to promote their growth. There are many things depending what type of filamentous bacteria you have there. Now, I'm not a microbiologist, and that, so really it's trying to keep them out. Importation of sludges I've seen can give problems, especially if they're importing from a site that has that issue already. All you're doing is spreading it around, and I've seen that happen several times. So trying not to, although it's an issue on one site, trying to treat the sludge elsewhere is only spreading the problem. So it's a difficult thing that better minds than I still have problems with.
Right, okay. The next one is the oxidation ditch you talked about control the ammonia to 12 milligrams per litre against a 0 milligram per litre consent. I'm not sure whether that's correct, but it's obviously a low consent.
It's a 20%, yeah.
Yeah. Could the RTC actually control closer to the consent so more energy savings could be made?
Yes, but that's really down to the site manager and scientific staff. Whatever they feel comfortable with setting as the limit, the target value that the real-time control system actually achieves. There should always be a bit of headroom, especially if you've got a site that's subject to shock loads, even in oxidation ditches, which tend to even those out. You want a bit of headroom to allow the system to balance out after it's been hit with a shock load. Again, it's always that consent, that target value of ammonium is always discussed with the site, and it's whatever the site feels happy with at the outlet. So it's really a site-specific value that we put in there.
Okay. The next one, with selector zones, how important is the internal recirculation?
Selector zones as such don't need internal recirculation. They are there with the mixing the return activated sludge and the sewage coming in. They're there to give the heterotrophic bacteria a chance to outgrow the filamentous and prevent them predominating. When you're putting an internal recirculation into that zone, you have to be quite careful, because what you don't want to do, as I said in the webinar itself, you don't want to introduce too much oxygen in there and just negate the site, negate the anoxic nature of the site. So if you've got high DO at the point that you're taking the internal recirculation from, there's no point in actually returning that to an anoxic zone, because you're going to put so much oxygen in it. You risk going above the 0.3 milligrams per litre and stopping denitrification. You will still get denitrification from the liquor in the RAS, but you won't get at that. In those conditions, it wouldn't be effective to introduce internal recirculation.
Okay, thanks for that one. The next one. How accurate are the nitrate and ammonium monitors? For example, are they sensitive enough to control for sites with 1 milligram per litre permits?
Oh yes, I mean we would range the analyzer according to the site and where it is. Speaking of here, we're talking of oxidation ditches. We would go to a low range system, which has a trying to think off the top of my head, it's less than its limit of detection is less than 0.1 milligrams per litre, and in fact the very low one I think is 0.02 off the top of my head, but I'd need to look at the data sheets. But yes, we can do that. For those low levels though, I would use an analyzer rather than a probe, because probes are prone to drift, and they're great for trending, but if you want them to be accurate, they need they need an awful lot of manual intervention, regular calibration, cleaning, checking like this, whereas an analyzer calibrates itself, cleans itself every day. When you're talking for really low levels, I would always go for an analyzer rather than a probe.
Yeah, I think a control system is only as good as its reading, isn't it, really, that it's controlling against. So.
Exactly.
The next one, how important is having separate mixers in order to achieve maximum energy savings through your nitrification, denitrification controllers?
The mixers are really important, because if you've, depending on the aeration system, if you're using fine bubble diffused aeration, then you'd need those anyway to create the velocity around the ditch. If you're going to turn down or turn off the rotors, then they need to be present to move the mixed liquor around the ditch and create and move mixed liquors from aerated to anoxic zones if your desire is to create those.
Okay. The next one is, I think, more than a comment, more than just a comment, really. And I think the person here is looking to see whether you agree or not. Low DO means slower filamentous growth, question mark. Would you agree with that? No,
I think it's the other way around. Low DO, low F to M ratios produce enhance the growth of filamentous bacteria.
Right. But the F to M ratio isn't affected by the DO concentration?
No, it's the food.
Okay. So there's no relationship between DO concentration and filamentous growth?
I've heard it said, I've not seen it in literature, although I've not had done an exhaustive study of that, but as I understand it, I think it tends to promote them, but it's more the F to M ratio is more the controlling factor or the promoting factor.
Okay. We have another 4 questions here. The next one is, do you have any advice for conversion to alternating ditches?
Is that, I've seen something of using putting ditches in series, so one operates aerobically, one operates anaerobically. I've got no experience of that, and that's quite a drastic change from the ditches that I've seen, which are operating mainly aerobically with hopefully with some anoxic zones in it. I've not seen it done, although I have seen it in some advertised literature.
Okay, so we can't. Maybe we take that
I can't
one
really comment on that. I
and,
can't really.
yeah.
I can't really comment on that one.
Yeah. So the person who asked that one, we'll see what else we have on that. We may well come back to you. How will performance for the ditch be affected when used without PSTs? Primary settlement tanks.
Yeah, they can be used with that, but you're introducing a lot more obviously BOD load into the ditch, so you've got a high carbon in there, so you'll be putting in a lot more oxygen. Obviously, just to treat with that, you're just going to have to your energy. You're putting a lot of carbon into the ditch, a lot of BOD into the ditch, so it would be the energy savings might be negated by just having to treat that. Depends on the location of the plant as to whether it's possible to use primary settling tanks if they exist and remove sludges to other sources.
Right, okay. The next one, what level of calibration and maintenance does the RTC system require?
Once it's set up, there's a period when we look at the performance of the system. After that, it's just periodically reviewed. We can offer sort of data, looking at the data as a service offer every maybe 3 months and giving a report on the performance of the RTC and any changes that may be needed to adjust it to match the conditions that may have changed within the plant.
Okay. The next one is there a lag time with the analyzer? I think we're talking ammonia and nitrate here, but I'll let you answer that now.
Right. It depends on the technology used. As I prefer the analyzer, the ammonium analyzer. Yes, there is a short delay. The analyzer would be taking samples, for instance, if we're talking about our ammonium analyzer, the ANTAX, then that would be taking samples every 5 minutes. Now, generally, that's sufficient. Nothing's going to change that quickly, especially in a fully mixed system like an oxidation ditch. You'll be seeing the trends. Probes will react faster, obviously, because they're direct in there. But as I said before, they are not as accurate and prone to drift and need a lot more attention. So you have to weigh up the 5 minutes or so delay between readings, and generally that certainly in ASP plants that's not a problem, and so I wouldn't have thought that would be an issue with an oxidation ditch where actually any spikes, load peaks that are entering the ditch itself are being diluted quite considerably by the mass of the liquids already in there.
And nitrate?
Nitrate, Nitrate, the nitrate probe, if we use the NITRATE, is almost instantaneous. Again, you can set to prevent sort of noisy values or the odd spike you can average over a period of minutes. But yeah, you can take a value every minute, 30 seconds from those, and they're instantaneous.
Okay, and the last question we have here, again, I'll try to interpret this. For sites with ultra-low P consents, phosphorus consents, can we still use ammonium and nitrate analyzers?
Oh yes,
we're talking about a separate issue, aren't we here? But yeah.
Yes, right. So what I was concerned about there is that when an oxidation ditch is running full tilt most of the day or all of the day, you especially in areas that are low alkalinity in the natural waters, then it's possible that you could be running close to exhausting the alkalinity and hence have pH issues. Now, with the low and ultra low pH consents that are promised, by dosing ferric or ferrous or aluminium salts, these are all acidic, so their effect is actually to consume even more of that alkalinity. And I'd also point out, and again that's been mentioned in previous webinars, that the amount, the proportion, should I say, of metals precipitant that you're adding is not increases as the concentration, the target concentration reduces. So the ratio at, say, if you're trying to achieve 0.5 milligrams per litre, the ratio of iron to phosphorus there is less than when you're trying to achieve, say, a 0.1 milligram per litre. You'll find that you'll be dosing proportionally a lot more metal within the to achieve a 0.1 in proportion to what you would have achieved to a higher concentration.
Okay. So we have one more question that's just creeped in. Can sites with low ammonia consents, 2 milligrams per litre, do the analyzers still have a benefit for real-time control?
Oh yes, even more so, because the maintaining compliance, you have a 2 milligrams per litre. You need to be ensuring that you are within compliance, and there's still energy to be saved there. I mean, if you perhaps target the RTC for putting a number over there, say 1 milligram per litre, then that's fine. But if you suddenly get a rain event or storm where you're after a dry period where you suddenly push in a lot of load into that plant, then you want that system to ramp up to deal with that ammonium. So yeah, in my view, it's even more critical on a plant that's got a very low ammonium consent to monitor it as it exits the ditch, or actually in the ditch, rather than monitoring it in the final effluent when it's too late. There's nothing you can do about it. At least if it's in the ditch, then you have a chance to treat it.
Okay, great. Thanks, Martin. I think that brings us to the end of our questions. Just like to thank you again, Martin, and thanks for everyone for all your questions. There was a load of questions there, which I think emphasises the fact that I think everyone found it a very good and very enjoyable webinar this morning.
Thank you.
Just wanted to remind everybody that we have our next webinar in our series. The details are on the screen now. It'll be on the integration of control systems. So that will be covering how we integrate the control systems that we have available at the moment, and more importantly, how we look at the visualization of the readings that come from that. That's to be held on Tuesday, June the 27th, so only in a few weeks' time, at 10 a.m. again. We'd very much like you to join us and ask you to forward your invitation to any colleagues that you may also benefit from attending. As we go through the webinar series, we have more and more people join, which is always a good thing. Finally, we do record all our webinars. I noticed that a few people joined late this morning, which is obviously very understandable, but don't worry if you did. you'll be able to watch all our webinars on the HACH YouTube channel. Our previous webinar, long title coming up, European Lessons for the New Low-Level Phosphorus Consent in the UK. That webinar is already available on our HACH GmbH YouTube channel. So if you've missed that or you want to have a re-listen to that, that's already available. So that brings us to the end of this webinar. I'd just like to thank everyone again for attending. Thanks to Martin again for a great presentation this morning. And we look forward to speaking to you all again very soon. Thanks a lot.